35 million years ago, a meteor slammed into what's now northern Russia, releasing more energy than 100 million nuclear bombs. The result? A geological jackpot, the largest diamond deposit ever discovered. It's real, it's massive, and yet it's never been commercially mined. In this video, we'll explore how a cosmic collision created trillions of carats of diamonds, what makes these impact stones scientifically extraordinary, and why this vast deposit remains completely untouched to this day. The cosmic collision. To understand this story, we need to step back 35.7 million years to the late Eocene epoch. Picture a warmer Earth, about 4 degrees hotter than today. Tropical forests were shrinking and grasslands expanding. Early primates and hoofed mammals roamed this changing world. Into this ancient world came catastrophe. An asteroid roughly 5 to 8 kilometers wide came screaming through the atmosphere at 20 kilometers per second. That's 45,000 miles per hour. Its target? A region in northern Siberia, rich in graphite-bearing Archean gneiss, ancient metamorphic rock formations over 2.5 billion years old that contained abundant carbon in the form of graphite. The collision created what we now call the Popigai crater, a 100-kilometer-wide scar that's tied as the 4th largest verified impact structure on Earth. But this wasn't just any ordinary asteroid impact. The target rock contained massive amounts of graphite, and that cosmic collision was about to perform the ultimate high-pressure experiment, one that would create diamonds unlike anything found elsewhere on Earth. The Diamond Factory. When that asteroid hit, it generated pressures between 35 and 60 gigapascals. A gigapascal is a unit measuring extreme pressure, and this amount is the equivalent to being buried 1,000 kilometers deep. Temperatures exceeded 1,600 degrees Celsius. To put that in perspective, that's hot enough to melt copper, and the pressure is equivalent to being under crushing rock that is 113 Mount Everests tall. In those extreme conditions, something remarkable happened. The carbon atoms in the graphite were literally squeezed and heated into a completely different arrangement in microseconds. This process, called a Martin-Sittig transformation, is a rapid structural change in materials under extreme conditions. It forced the carbon into 2 distinct diamond structures. The first was regular cubic diamond, the kind we're familiar with, but the second was something far more exotic, hexagonal diamond, or Lonsdaleite. This material is named after the crystallographer Kathleen Lonsdale, and early computational models predicted that Lonsdaleite could be up to 58% harder than diamond under ideal conditions. Think of it this way: if regular diamond is like spheres arranged in a cubic pattern, like the corners of a box, Lonsdaleite is like the same spheres arranged in a hexagonal honeycomb pattern. This different atomic arrangement gives it properties that make materials scientists absolutely fascinated. But here's the crucial detail. Recent laboratory measurements have recorded Lonsdaleite with Vickers hardness values of approximately 164 and 124 gigapascals, but exact values vary. The Vickers scale measures how hard it is to scratch or indent a material. While we used gigapascals earlier to describe impact pressure, here it measures resistance to deformation. This compares to cubic diamond's 80 to 120 gigapascals. While these are under ideal laboratory conditions, it is likely a meaningful improvement over existing materials. The impact created special types of melted rock that formed when the asteroid hit and mixed everything together. These rocks trapped the tiny diamonds in microscopic clusters, but only in a narrow zone around the crater where the pressure was just right and the cooling happened fast enough to freeze in the diamond structure before it could transform back to graphite. The frozen treasure. Now you might be thinking, with 10 trillion carats of the hardest material on Earth just sitting there, Russia must be racing to dig it up, right? Well, that's where our story takes several unexpected turns. First, let's talk about location. The Popigai crater is 300 kilometers east of the tiny outpost of Katanga and 880 kilometers northeast of Norilsk, and those are already some of the most remote places on Earth. We're talking about the high Arctic, where temperatures plummet to -40 degrees Celsius. The ground is locked in permafrost for most of the year, and there are literally no roads, no power lines, no infrastructure whatsoever. It's so remote that the nearest major national railway link is about 2,000 kilometers away. To put that in perspective, that's like trying to mine diamonds in Detroit and having to ship everything to and from Miami, except that entire distance is across undeveloped, unforgiving wilderness with no gas stations, no rail lines, no food supplies, and not even basic shelter. But isolation isn't the only barrier. In the 1970s, Soviet scientists made a fascinating discovery about these diamonds, and then immediately classified the entire deposit as a state secret. Why? Because at the same time, the Soviet Union was heavily investing in synthetic diamond production, and they didn't want to flood the global market or undercut their own synthetic operations. Today, the economics are even clearer. Synthetic industrial diamonds from China can sell for as little as just 25 cents per carat, making the expensive extraction from the Arctic economically questionable. And here's another issue. Most Popigai diamonds aren't gem quality. They're tiny, flawed, often yellowish, and primarily useful for industrial applications. While that might sound disappointing, it's actually what makes them potentially revolutionary. These aren't diamonds for engagement rings. They're diamonds that could be used to cut through the hardest materials known to science. The nanopolycrystalline structure means they're made of countless tiny crystal grains all fused together. Combined with the Lonsdaleite content, this gives them abrasive properties that are 1.5 to 2.4 times better than synthetic monocrystalline diamonds, which are made of single uniform crystals. The game changer. While Russia has been sitting on this deposit for decades, the materials science world has been racing ahead. Recent breakthroughs have completely changed what we know about these ultra-hard materials. In recent years, lab teams have produced high-purity hexagonal diamond and reported Vickers hardnesses substantially above typical cubic diamond values in some tests, tens of % harder in some measurements. But results vary, and the field is evolving. This breakthrough raises a fascinating question. If we can now make Lonsdaleite artificially, does that make the Popigai deposit obsolete, or does it actually make it more valuable? Consider this. Recent studies from 2023 using advanced X-ray diffraction and Raman spectroscopy have revealed novel microstructures in Popigai diamonds that we're only beginning to understand. These techniques analyze how materials scatter light and X-rays to reveal their atomic structure. These natural impact diamonds contain complex mixtures of cubic diamond, Lonsdaleite, and graphite in arrangements that we can't yet replicate artificially. Think about the applications: drilling through ultra-hard composites for aerospace, polishing semiconductors for quantum computers, or cutting materials for fusion reactor components. As our technology advances, the demand for super-hard materials is exploding. Nature's laboratory. The Popigai meteor impact holds significance far beyond materials science. Some researchers have explored links between Popigai and late Eocene environmental changes, but any tie to the Eocene-Oligocene mass extinction is disputed. An impact of this magnitude would have dramatically altered Earth's climate and ecosystems for quite some time. This connection makes the Popigai impact site not just a materials science treasure, but also a window into understanding how asteroid impacts shape life on Earth. Every diamond grain contains information about pressures, temperatures, and conditions that existed for mere microseconds during one of the most violent events in Earth's recent geological history. And it happened so fast. Unlike natural diamonds that form over millions of years deep in the Earth's mantle, these impact diamonds were created in microseconds. The shock wave compressed and heated the graphite so quickly that atoms didn't have time to arrange themselves into the most stable configurations. They got locked into these exotic, super hard structures instead. It's like nature accidentally discovered the recipe for the ultimate super material and then hid it away in a remote frozen wilderness. The future of super materials. So what's happening with Popigai today? The site remains largely untouched and protected. The area is off limits, and genuine Popigai impact diamonds are very rarely available for purchase. They're extraordinarily rare to see in person. But that might be changing. As synthetic diamond technology advances and our understanding of supermaterials grows, there's renewed scientific interest in these natural impact diamonds. Researchers are studying them not necessarily to mine them, but to understand how to replicate their unique properties artificially. It's also possible that the demand for ultra-hard materials could explode in the coming decades. With the rise of quantum computing, fusion energy, space exploration, and advanced manufacturing, we might desperately need materials with properties that only these impact diamonds possess. The Popigai crater represents something profound about our planet. Earth's vast geological history has provided countless natural experiments where extreme conditions create materials we're only beginning to understand. While we've learned to synthesize many diamonds, the specific nanostructures found in impact diamonds remain largely beyond our technological reach. These diamonds demonstrate unique luminescence properties. Luminescence is the ability to emit light when excited by energy. They also have structural defects that make them valuable for research into carbon nanomaterials, a field that could revolutionize everything from electronics to energy storage. Perhaps the real treasure isn't the diamonds themselves, but what they teach us about pushing the boundaries of materials science. So there you have it. One of nature's most violent experiments created Earth's largest known diamond deposit, but we're not digging it up because it's remote, was kept secret for decades, and synthetic alternatives are cheaper to produce. Yet these impact diamonds might hold keys to creating the super materials of tomorrow. Nature's power never ceases to amaze and humble us. What other natural phenomena would you like us to explore? Share your thoughts in the comments, and don't forget to subscribe for more incredible stories about the forces that shape our world.